1 second. Hi guys. Assuming you can hear me. Yeah. So Temitayo, Daniel, Timineng, anyone goes, and I'm your, should I say, moderator for today, I guess. So I mean, I wouldn't say teacher, I would say moderator, because I'm just like bringing you into this. I'm not really going to go into anything advanced, or so. You guys are going to go into the advanced stuff from the next session, and so on and so forth. So I'm just here to like give you a soft landing into the course itself. Just like Shetal already said, you guys should be happy you guys like were accepted into this course, because I mean you get to like learn from the OGs, like the people that actually built the technology itself. So it's actually a big privilege to actually do that. So I'll try my best to keep it as long and as short as possible. If you at any point like it's easier to like keep it asynchronous in that way. And also you can raise your hand if you like want to like speak to ask your questions in a more audible way. And yeah, I mean, I was taught to introduce myself, but I guess I didn't do that. So I'm Timilane. I have been in the blockchain ecosystem for like 45 years now. I'm a smart contract engineer. I've worked at Avikochi, and I'm the co-founder of a bridge where I like teach people how to introduce them to like one and so forth. So enough about me. Let's get into business in this case. Yep, start by sharing. So for most of you that might have like low bandwidth, I might have to like turn off my video. So yeah, let's start. Give me a second to share my screen. One second. Okay. So today we'll be diving into like had this type of experience with like proxies, like understand exactly what they do and why we actually need them in the system. Before I like start, how many of you guys have like heard of proxies? I mean, not in the blockchain ecosystem, because I mean the word proxy actually is being used in a lot of different settings. So if you've actually heard of the word proxies, just like raise your hand, or yep. Sorry, voice is breaking.
Yeah, the internet is breaking a little. Hopefully, actually, it's okay
so
now.
Can someone just like confirm that?
No, I think it's okay now.
Yeah, interesting. Okay,
but go for it now.
You guys would have to give me a second then.
Sure. It's clear now. It's good now. Timilane, I think when your video was on, it was pulled, but now it's okay.
1 second.
Okay.
Got it. Yeah, I'm back. So I'm assuming this should be better now. Just switch to a fallback network. Perhaps because of the size of the call. So yeah, better, nice. So yeah, I was actually asking you guys if you've heard of proxy, the word proxy, not just blockchains, smart contracts, blah blah, like proxies. Nice. So a lot of people have heard of it. Nice, awesome. So Nishant and Victor and a lot of guys raised up there, and John Ode, Vijay, you guys have heard of proxies. Basically, I actually first heard of proxies in cybersecurity, and it's basically when you try to access a resource using a different endpoint. It's like you are trying to like get to a door, or you have to go through a door to enter a building. and then you have to actually, use another door to access that particular building. So basically, you have two doors that lead to the same building. The second door acts as a proxy. It acts as like, you can call it a second entry point to that building. Oh, Victor, your hands were raised for a question. Sorry, I told everyone to raise their hands if they're like, out of proxies. So, but Victor, you can ask your question. It's fine. Okay, sure. Yeah, so let's keep it. So basically, yeah, proxies sorry, 1 second. I'm trying to get this to work. Yeah. So proxies are basically just like someone just said in the chat, middlemen that are between you and the resource. They are like, oh, there's another way to access this and so on and so forth. So yeah, what we have discussed what proxies are. Well, in the general setting, we also discuss what they are when it comes to like smart contracts and stuff. We'll also be talking about delegate calls and common mistakes about that people make, because proxies are actually very important and also very dangerous when it comes to smart contracts. So let's get into it. So what is a proxy contract? Just like we said before, it's a contract that forwards calls to a logic contract while keeping on state itself. Now, for most of you that might not be familiar with how smart contracts work, every smart contract is an address, right? It's basically an address that holds code. And the code is what determines or what instructs how the data in it is actually being changed or mutated. For example, take an ERC20 token. It's a smart contract, right? You write a smart contract that is an ERC20 token, and the contract contains all the commands, the logic, how balance is being changed, and so on and so forth. And how events are being emitted, allowances, approvals, and so on and so forth. This logic basically, should I say, dictates how storage in that smart contract is being changed. So if I send you 10 USDT, right, I'm actually calling a function on the smart contract. And this function is maybe called a transfer or the transfer from function. It dictates how my balance on the smart contract will change. So if we bring all this together, we have like two things to talk about, right? We have logic. Logic is basically code, or in this case, solidity. And then we have storage. Storage is basically storage. It's basically what is stored in that smart contract. Storage is vast. I mean, it depends on what you actually define. And for most of you that are not, should I say, solidity agnostic, I mean, you have to be solidity agnostic to be on this call. So, yeah, storage is basically what you define in the smart contract. So when you define your state variables, you define your mappings, your non-immutable variables, and so on and so forth, then you are actually setting storage. Yeah, so back to this. We have a user that sends a transaction to the proxy, and the proxy delegates this transaction, this call data to the logic. Now, normally when you interact with a normal contract, you are just a user interacting with the contract. There is no proxy in between. So all the calls are basically forwarded. Sorry, I need to pause for a second to see if you guys are, questions and stuff. Oh, we recording. Yeah, I think I should actually start recording this. Oh, I think it's already started.
It's already.
Yeah, my bad. Yeah, resources. Yeah, you're going to get a lot of resources. Don't worry. And just trust me, I'm going to try and, patch this up with a lot of examples, not just me reading from the PPTX. So it's actually, easier to understand like visually and stuff. So let's continue. Back to this guy. So when it comes to proxies, right? The proxy in this case is basically the middleman. So instead of the user interacting with the contract directly, he interacts with the proxy, and the proxy uses its own code to change storage from the logic contract itself. Now you might ask, why exactly do we need all this, chaotic processes? When you write smart contracts, you have to deploy them, right? You deploy them on any network you want to, Ethereum, Binance, Smart Chain, Polygon, Arbitrum, and so on and so forth. And the issue is, after you deploy a smart contract, you can't make changes to it. There's nothing like, oh yeah, I forgot to add a function. Let me just, change this. It's immutable. It's gone. It's there. There's nothing you can do to actually change the code or the logic that has actually been deployed to that contract address. So it's actually a good thing and also a bad thing, right? A good thing in the sense that it's basically what the blockchain is all about, immutability. You can beat your chest and say, yeah, my code is immutable. I can't do anything to change it. So you can trust that the code will never change. It's fine. It gives users the trust they want. And it's also bad in the sense that once you actually make a mistake, right, in your code and you deploy it, boom, that's all. There's nothing you can do to change that, unless you, of course, redeploy that, which is chaotic in some sense. Like, some of your users might not want to migrate to the new contract you deploy. So, sorry, which is, very bad. Now we have the proxy contracts. The proxy contracts are actually, introduced to actually make upgradability easier. So normally you would have a smart contract that is deployed, right? And you would have users interacting with that smart contract. The smart contract contains the code that is used to, mutate its own storage. Good. But now you have a proxy. And how does the proxy work? Let's look at the rules. The proxy stores all states, right? It stores all the balances, the mappings, the variables, blah, 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 everything. That's basically what it stores now. The logic contract holds code, right? It does not have any state. I mean, you can argue that every contract has its own state, that is storage, but you can decide to not use it. This is what the logic contract is about. From the name, logic, it only provides the code necessary to mutate storage on the proxy. Normally, the proxy would serve as the logic contract and also the storage contract, right? That is, it uses its own code to mutate its own storage. But once you actually want to, use upgradability and, introduce proxies, the proxy contract would only hold storage, but it's logic to another guy called the logic contract or the implementation contract. So the logic contract holds only code. It has no persistent state of its own. MSG.sender is preserved, MSG.data is preserved, MSG.value is preserved. But from the user's perspective, they will always be talking to the proxy. And swapping the logic contract leaves all stored data completely intact. Now, this is where upgradability comes in, right? When you swap the logic, this guy still retains his data because, you are not interacting with this guy. You are just changing this guy. Now, this might seem a little bit, chaotic for now, but let me check the messages just to make sure I'm not missing anything. Yeah, a lot of discussions in the messages, but yeah, I'll keep going. Yeah, so now that we are actually done with the rules, let's go to why we actually want to use proxies. Note that we'll still go deeper into this. Upgradability, of course, yes, 100%. This is exactly what people want to use proxies, because if you go back to this diagram, the proxy doesn't change. You can't redeploy it. That's the point. You can't redeploy the proxy. but you can always keep changing the state, that is the storage. The only thing you need to do is redeploy the logic contract or the implementation contract. This guy uses its own code to change the state here. So since this guy is, expendable, it is changeable, definitely this guy is now upgradable. In the sense that you are not actually redeploying the proxy, you are redeploying the logic contract. So if you don't like the way something was implemented, maybe you wrote a function, swap. Let's call the function, swap. And the swap function actually removes a 10% fee from the sender, right? This is defined in the logic contract. But the mapping that tracks the balance of the user is actually stored here, right? And maybe you have a DAO vote, or users are like, no, we don't want the fees, blah, 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 blah. Okay, now you can actually remove that particular logic or that line from this guy and redeploy. So you can redeploy this guy, bind it to the proxy, and boom, you have upgraded it. That means after the upgrade, users won't be charged the 10% fee. Basically, your upgrade is successful. You've basically upgraded this guy. Yep. Hence, upgradability. So it allows you to fix bugs, ship new features, and you do not need to redeploy the storage contract. That is the proxy contract. All the balances, everything on chain stays exactly where they are, which is on the proxy. Now, code reuse. This is basically BLOK Capital's, should I say, feature in this case. So how do you explain code reuse, right? Now, notice here, you see that we have 3, should I call them actors here? We have the user, the proxy, and the logic, right? We have established that the user is the guy that interacts, that is you and I, right? The proxy is the storage contract, the one that holds all the states, all the variables and stuff. And the logic contract is the one that contains the code to mutate the storage. Now, when it comes to code reuse, it means that we can actually use a logic contract for multiple proxies. So far, the proxies all have the same storage layout. If you understand what I'm saying, that means instead of us deploying multiple logic contracts, you can basically have your proxy contracts, like 50 of them, and have one logic contract. That means this guy is basically mutating the storage of 50 contracts. It's just providing code, providing instructions of how that particular storage should be mutated. That is what code reuses. And BLOK Capital literally does this because each garden in this case is a proxy. So the facets are distributed for each garden. Nice. So let's continue. I'm assuming maybe you have questions. We'll take that towards the middle of the class. And finally, lower deployment costs. Yeah, for this is actually for some certain sets of proxies. Like for example, the Gnosis safe. I'm assuming most of you have heard of multi-sigs, like the Gnosis safes. Gnosis safe uses the the minimal proxies, and they're just like proxies that literally have the most minimal set of bytecode. We will actually see some examples. So yeah, this is some of the reasons why we would actually use proxies. Now let's talk about this, guys. These guys are actually very important if you actually want to understand proxies at the most the best levels. Normally, I'm assuming you guys already know about core data, selectors, signatures, data locations like memory, blah blah blah. But let's just go over it for everyone to be on the same page. Now, when you interact with a contract, right? Say you call a function, you're actually performing a low-level call under the hood. And the low-level call is basically you just, calling the function name and passing the argument types. Now, for example, we have this function that is very, very, popular for ERC20 tokens, the transfer function. It's transfer, you pass in the address store and the UN256 amount, that is, who do you want to send this token to, and how much or how many tokens do you want to send. Now, when you call this function, you are basically, executing this call data, or should I say, sorry, this selector. You see, when you actually compute the hash of this guy, you get something called a function signature. It's like a 32 bytes. When you hash something, hash any data, you actually get a fixed amount of data as outputs. In Solidity, it's 32 bytes for catch capital 5.6. And when you actually, downsize that 32 bytes of function signature to 4 bytes, you actually get the selector here. And this selector is basically like a function ID. So basically, if you search up OXA9059CBB on, I don't know, any selector library, then to basically return the transfer function for you with these argument types. Now, you might be asking, why exactly are we talking about function selectors or function signatures? It's because when you actually deal with proxies, proxies need to know exactly what call to forward to their implementation. Because if you remember, this guy needs to forward the call to the logic contract. So this guy, the proxy, needs to know exactly what to forward. And it's not going to forward everything. It's just going to forward like a compact version of the transaction or the function call. This might all sound like gibberish, but don't worry, you'll get it. So data locations for this, we have core data. Core data is basically for external calls. Say, for example, a contract wants to interact with another contract, right? If he's sending a lot of data, like strings or bytes, then they actually stay in core data. It is actually much cheaper, but it is read-only, which means whatever is stored in the core data section cannot be written to. It cannot be changed, right? Cannot be mutated. Then we have memory. Of course, everyone knows what memory is. It's basically that guy that doesn't take a long time before it clears up. So basically, memory is, when you call it function, right? At runtime, memory is what you write into or what you read from, and immediately the function is done or the transaction is finished, memory is wiped clean, right? And finally, storage. Storage is what this guy stores. It is basically persistent state, right? It is permanent. It is what you can change, what you can write to and read to. An example is in an ERC20 token, the balance mapping that tracks everyone's balances. That is storage, because you need it to persist over transactions, right? Let me move on to the dispatcher. Now, we understand that proxies, according to this diagram, need to interact with the logic or implementation contract. How do they do that? They do it through a dispatcher. Now, most of us order food, and they're like, oh yeah, the dispatch rider is 2 minutes away, 30 minutes away. In this case, the dispatch rider is just a guy that went somewhere to collect your food and, came back to give you your food, like just came to deliver the food to you. You might not even know what the food actually contains. Just like, come here, take the food, give you the food back. But when it actually comes to the proxies, right, the dispatcher is this guy that's, takes care of taking the data that the user actually sends to the proxy to the logic contract. So the user sends a transaction, the proxy strips that transaction, gets the call data from that transaction, and dispatches it to the logic contract. The logic contract uses its logic to, execute that call data against the storage of the proxy. Sounds like gibberish, right? Let's just continue. Now, let's look at this code line by line, right? We have a simple structure, yeah? And sorry, give me a second. I want to see if I can use an annotation tool here. So I should be able to like annotate on the screen. 1 second. Good. Oh yeah, I can't do that. Yeah, that makes sense. So now we have address public implementation. This implementation is also the deployed address of your logic contract here. The proxy needs to know where this guy is deployed, so it knows exactly where to forward the call to, right? Now that is called the implementation contract. And now let's just say we have the constructor, we pass in the address of the implementation, and then we set it in storage. Now we have fallback, right? What is the fallback function in Solidity? Basically, from the name fallback, it's basically what gets executed when you try to call a function that does not exist on a contract. So say, for example, you have an ERC20 token contract. You know the functions there, like transfer, transfer from, balance of, name, symbol, approve, and so on and so forth, right? Now, say, for example, you now try to call the function swap. The function swap does not actually exist on that contract, so it's going to trigger this guy. If this guy is actually, defined, if the fallback function is defined, then it triggers this guy. That means that for a proxy, the fallback function will always be triggered because the proxy contract does not, most times they don't contain any function, if you get what I'm saying. So that means once the user interacts with the proxy by calling a certain function, this guy will be triggered because the proxy does not contain that function in its code. So let's now see what happens in this fallback function block. You will load the implementation address to memory here, and then we enter an assembly block. We actually, execute a call data copy. Call data copy is basically an opcode. And it's basically allows you to copy call data into memory starting from position 0. Position 0 means copy all the data. Do not start from the middle, don't start from the end. No, start from the beginning and copy all the data to memory. So remember we talked about call data here, right? Call data is the raw bytes of the incoming transaction. So that means if a user calls the function balance off, right? Function balance off is converted to, this guy, selector, and whatever you actually, pass to it. Everything combines to call data and is stored, of course, in call data. Now, call data copy is actually copying that, call data to memory. Good. The next thing is we now execute a delegate call. Now, we haven't actually defined what a delegate call is, right? So let's just go through this code and then we will define that later. So we have let results is equals to delegate call gas. This is also an opcode which literally forwards all remaining gas to the current call context. Implementation is basically the to address, that is which address should we forward this call to. Remember that the implementation address here is the address of what? The logic contract. Good. Next, we have 0, call data size, that is the total size of the call data you copied, 0, 0. I'm not supposed to go very, very deeper, like very deep into this, but we are still going to do some deep analysis regarding code itself. And then this is basically a delegate call that runs against the implementation. Then we have return data copy. Basically, if this call returns any data, then get it back and store it in memory. And then check if the call actually, succeeded or it reverted. Basically, this is what this does. So this is the dispatcher, right? This dispatcher does just 3 things, or should I say 4 things. It copies whatever data was sent to the proxy into memory. It executes a delegate call with that data against the logic or implementation contract. Then it gets any output data back and, you know, bubbles it up. Now, let's define the difference between call and delegate call. Remember that we used delegate call here instead of call. Call is basically what you do when you interact with the contract directly. So let's assume you call the contract, you do the function balance of, that's a call. You do the function transfer, you call that against a normal contract, that's a normal call. And the difference between call and delegate call is that, sorry, when this guy does a delegate call to this guy, or should I say when this guy does a call to this guy, this guy contains code and also contains state. So if it does a call to this guy, then this guy is actually going to be using code, its own code, to actually mutate its own state. Simple. But when this guy actually does a delegate call to this guy is actually using this guy's code, the logic contract code, to mutate its own state. That's basically the difference. Hence the name delegate call. Delegate call means the proxy is trusting the logic contracts to actually contain a correct code that can be used to mutate its own storage. Checking if there are like any gates, any calls. Yes, exactly. Dan Yosemi. Delegate calls means I'm using my storage, but I'm using your code to mutate my storage. That's all. It's simple. VJ, if the call data includes the function selector, when is the delegate call picking the values that will be used? Yeah, you see, the call data is a combination of the selector itself and the data. I would have loved to actually, you know, use an example for you guys here, because give me a second. So let me see if I can encode some stuff here. Signature database. Give me a second. To use encoder. Yep. Okay, so I'll be sharing a tab. Just, you guys should just tell me if you can see it. So this is a tool I've been working on. It contains some stuff, but I'm still working on it, of course. So can you guys see the tool?
You might as well zoom in a bit. Well, actually, everybody can zoom in, so no problem.
David,
no, keep it as it is.
Daniel.
Sorry, my bad.
The funniest thing is I can't even see the emojis you guys are responding with, but I'm assuming you guys can see it, right? Okay, so now the example is transfer, right? A function transfer that accepts an address, isn't it? And a number, right? So now, if we want to generate the call data for this, we need to, of course, you know, pass in an address and, of course, a number, right? So let me get a sample address here. 1 second. Good. So let's say we have this address and we have this number, right? This is basically call data for this call. Does that make any sense? This is basically call data. So if you look at this call data, you can see that the first 8 bytes, the first 4 bytes here, A9059CBB, is basically the function selector for transfer with this particular, you know, input types. And the rest is basically this guys being encoded. If I change this, you see that the call data changes. If I change this, the call data changes. So what this guy does is that it forwards this entire thing, you understand, this entire call data to be executed against the context. It gets into its own context, but it uses the logic of the implementation contract. Does that make any sense? This is like just for you guys to see what call data looks like. Yep, okay, so back to our presentation. Now, Now that we have established what core data looks like, and we have, to some extent defined what delegate core is, we can continue. So I might not be able to live code this, right? But let me see this. Okay. I will try to give you guys another example here. So this is a task for, anybody. I want you guys to just go on Etherscan and find me one contract that is a proxy, any type of proxy, like any type. I just want a contract that is a proxy. That's all. No, I need a contract address.
Should we do
you need to actually paste the contract address here, actually. I just need a yeah, I know USDC is a proxy, but I need the contract address and of course the network. Okay, Musa, what network is this guy? Etherscan, right? Like minutes. Nice. Stepolia, are you kidding? No, I don't want test networks. No, I want like main networks. Nice. So David got us, let me see, what contract is this? This is, this is definitely a proxy. So let's take a look at, should I use my tool or should I use Etherscan to actually interact with this? Let me use my tool. Okay, 1 second. We have source tools, Explorer, serial. Okay. OXAOB, OXX0B, yeah, that's correct. So just give it a little bit of time. Okay, so now this is basically, I think this is the USDC contract, if I'm not wrong. And as you can see, it's EIP 1967, which is the transparent proxy. We don't know what that means yet, but we are going to find out. Now, this is basically an all-in-one. It's basically, it's if you look at the compiler version, 0.4.24, which is very old. So this is flattened. So we might not get what we need here, but let us use to, share this tab. Now, if you look at this contract on Etherscan, you can read contracts, that is, you can call the read functions, and you can write contracts, that is, you can call the write functions. But you can also read as proxy and also write as proxy. Now, if you check the read contract, you see that there are just two functions there, the implementation function and the admin function. Basically, this one returns the address of the implementation contract, and this one returns the address of the admin. Now, if you read as proxy here, you can see there are a lot more functions there. Now, note that this and this are basically two different contracts, right? Because OXA0B is the proxy. This is the immutable contract, the one that holds the states. While this is basically the implementation contract, the one that holds the logic. Hence why you can see like there are a lot of more functions there. And anytime you call a function like total supply, it is not fetching this data from this guy. No, it is fetching it from this guy using delegate core. If you get what I'm saying, that's exactly what it is doing. Now, we're definitely going to look into more complex examples, but this is basically what a proxy is. So that means that if the owners of this contract want to change anything, they just need to redeploy this guy. While this guy will keep its contract address, and that's all, upgraded. Nice. So can we unbreak our protocol if storage slots? We are going to talk about storage slots later. Yeah, L Ochin, I think you have a question. Yeah, sure.
Hello. So I want to ask about the the censorship resistance about this one? Because like
Yeah, I'm muted, but I can't hear you. I don't know if
you can't
it's
hear me?
just me.
Hello?
I think I can hear him. Maybe you're on mute, Timbaland.
Or maybe you can just like send to the chat.
Yeah.
Yeah, that'll make sense. Okay, so thanks for that example. Let's go back to the presentation. No worries, we'll be doing like some examples too. So now, storage layout collision. Now, this is actually very important, right? When you are dealing with proxies, a lot of people have actually gotten this wrong, and it is actually very easy to get wrong, and it is very disastrous if it happens. Now, we agreed that we have two contracts, according to this guy. We have the proxy contract and we have the logic contract. The proxy stores states, it contains all the variables that need to be changed, and the logic contains the code that is used to change the state. Now, there's a big problem, right? If the logic contract or the implementation contract is used to change state, it must know about state. It must know the structure of this state, right? Because if it doesn't, then it can't change state. Now, take for example, this guy. Let's assume that we have a proxy that has this state variables. That is total supply in the first slot and owner in the second slot, right? Now, if this is what we have in the proxy, and we have an implementation contract that's basically now defines its own like this. That is, instead of putting total supply in slot 0, I'm putting owner in slot 1, it reverses it, then it is going to corrupt state. Because when this guy makes a delegate call to this guy to change owner, it is going to assume that owner is at slot 1, whereas the logic that was written in the implementation contract is going to assume that owner is at slot 0, which means it will be overwriting total supply on the proxy. Does that make sense? Oh, Harrison, you didn't get my explanation on the readers. Okay, this is what I'm saying. Just give me a second. Let me go back to the start. So we have a contract, right? We have this smart contract, and this is the code for that contract. The smart contract is deployed at this address. This is the contract address, OX, AOB, A0B, blah, 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 right? And this is the address. But this contract is actually a proxy, which means that you see this code right here is not really being used to, mutate its own state. Funniest thing is that this contract is an ERC20 token, which means it contains a lot of data like balances, approvals, name, symbol, blah, blah, blah. But it is not using its own code to change its own state. Whose code is it using? It's using this guy's code. Now, OX435 is an implementation contract. Actually, it is an implementation contract. And you say the previous contract we came from is actually using this guy's code to change its own state. Hence, when you come to the proxy contracts here, this guy, and you read as proxy, and you do something like maybe post, and it returns false. This false is not being read from this contract. It is being read from the proxy. Does that make sense? Yeah. Oh, wait, you said he's audible. That's weird. Can someone unmute and speak, just to confirm? I just want to make sure I'm not,
Can you hear me?
Jay, you are muted, but I'm not hearing you. That's weird.
Can you hear me? Can you hear me?
You're muted, but I can't quite hear you at all.
Can you hear me?
Yeah, that's weird. Give me a second. Got it. Yep. I think, yeah. Sorry. That's what you get when you use Linux. So you guys should, I can hear you now. Sorry, I was actually on the wrong audio profile.
Okay. Can you hear me?
100% I can hear you, Jamil. My bad. So yeah, I think we can go back to our presentation now. So now we're talking about common mistakes being made when you are using proxies. So we have talked about layout collision. This is actually very common and it is deadly because once it happens, you can't roll it back. Because once you write the value of total supply to the value of owner, boom, everything is gone. There's nothing like, oh, yo, sorry, let me just roll this back. No, that you don't roll back on the blockchain. So you have to make sure that your your implementation contract has the same layout as the proxy, so that when it makes changes, it knows exactly where it is writing data or reading data from. Now, constructors, when a user calls the proxy, delegate calls the logic, right? The logic constructor already ran during its own deployment. It never runs again. Most people try to use constructors for, what are they calling it? Constructors for implementation contracts. That doesn't make any sense. There's no reason to use constructors for implementation contracts. Instead, you use what? Initializers. Initializers are basically just functions like constructors, but you have to define them yourself and you have to explicitly call them when you are actually deploying them. That is why when you look at like Open Zeppelin's upgradable standard, you see initializer, initializable. I need to speed this up. Unguarded, this is actually one of the craziest ones. A lot of hacks have happened because of this. Most people actually, have the upgrade functions and make it unguarded. They forget to put a modifier like only owner, blah, blah, blah. And boom, an attacker basically just upgrades the proxy with their own implementation and, they take all the funds out of the contract. So always make sure that all your upgrade functions are guarded. Now, also, this also applies to this guy, the initialized contracts, right? The initialized functions. Always make sure that this can only be called once. A lot of hacks have happened because of this too. Okay, guys, we need to speed this up. So let's just recap. Remember, we talked about proxies. Proxy forwards the call to the logic contract, where the delegate calls, runs the logic codes in the process context. Everything is preserved, storage, and image is sender. We have the selectors, which I demonstrated for you guys. The initializer is what we use instead of the constructor, the call ones. The storage is, everyone knows what storage is, and access control. Everything must be gated. Everything must be gated. Since it is upgradable, then it must be gated. Now, we have to talk about the different patterns we have. But before I move on, let's see if we have, I can hear you guys now. So if you have any question, just, unmute and ask so that I can quickly, tackle that.
Sorry, sir.
Yep, sure, I can hear you.
Can you hear me, sir?
100%.
So my question is that you were mentioning about initializer and constructor. You mentioned that the initializer should be called once, right? And the constructor also, it's a kind of contract that, like, when you deploy it, it's deployed once. So
yes.
What's the difference between, like, I've already deployed once, which means I have called it constructor once, and calling the initializer once? Why shouldn't I use my constructor, and why initializer?
Good. So now you know that the constructors are single call functions, right? But that's not their only property. Their second property is that they are called during construction. That's why they call them constructors, right? They are called during construction. That is why you can use constructors to bypass things like checks that check if an address is a smart contract or not. Because when a constructor is being called, the contract is not yet a smart contract because it has not been deployed yet. Now, the issue is that when you put your code in a constructor for the implementation address, it is never called via the proxy. Because at that moment, the proxy doesn't see it as a smart contract yet. It isn't. That implementation contract is not a smart contract yet because it is, it is still being constructed, if you get what I'm saying. But if you actually define a function, right, that has to be called once, for this function to be called means the contract has been deployed, isn't it? And then you just make it, you put in a type of modifier to make sure that after it is called once, it can't be called again. That's the difference between a constructor and an initializer. Does that make sense?
Yeah, thank you, sir.
Yes. The only difference is a constructor is called when the contract is being deployed. That is, anything that happens in the constructor happens when the contract is in the process of construction. And you don't want that for a proxy. You don't. Good. So, yeah, I think someone raised their hand. Yeah, Jamie, you just unmute. Yep.
Yeah, thank you, sir. So for unguarded upgradable function, so most as a dev, if I notice that, okay, I have this error in my code, so what's the best way to implement to correct it, or I have to start all over again?
Well, the issue is, you see this function, right? The function upgrade to, that we used as an example. If after deployment, you notice that you forgot to maybe add like a modifier or a guard, the issue is there's nothing you can do because this function lives where? On the proxy. And you can't edit the proxy per se. You can't say you want to change code on the proxy because the proxy is not meant to hold code in the first instance, only the logic contract. So the best thing to do at this point is to basically just redeploy. You have to redeploy the proxy at this point. Does that make sense? Because at this point, there's nothing you can do. You can't say, oh yeah, I need to, redeploy, I need to upgrade. No, this is basically the proxy itself. So the only thing you have to do is redeploy.
Thank you, sir.
Yeah, you need another proxy for the proxy. Exactly.
Yeah, sorry, yeah, I'm raising up.
Yeah, sure.
Yeah, so in regards to his question, what of why deploying this proxy and you didn't add the checks for the access control, and maybe on the long run you already deposited money into the proxy. Does it mean at that point in time the money is gone? There's no way you can destroy the contract and retrieve your money from it, or just like that, your money is gone?
Well, I mean, to some extent, right, I'm going to agree with you. But it depends on exactly, I mean, let's use a real life perspective, right? You mentioned that, let's assume that this protocol, that is this proxy that has this bad code, right, already has a lot of people using it, maybe has racked up a lot of TVL, maybe $2 million, $3 million in tokens, right? And you finally discover that, damn, you forgot to actually guard this, this function. Now, this function is actually a way for you to, upgrade the implementation of the proxy itself. So the first thing you might want to do, I mean, especially if an hacker didn't see it before you, the first thing you want to do is you want to add a function that will allow you to rescue all the funds from the proxy. You can do that because, I mean, this function here is called an upgrade function. It allows you to, upgrade the proxy itself. So you might want to deploy a new logic or implementation contract that contains a function that can rescue those funds from the proxy. That should be the first thing you do. Once you do that, you call this function, you pass in the address of the new contract you just deployed that has that function, and then you bind it to the proxy, and finally you call the function. That way you are able to rescue the funds, and finally you redeploy your proxy from scratch. I mean, That way you now have the function, you have the funds, so you can start from scratch. And if they are user funds, of course, you wouldn't want to just like, get all users' funds without asking them. But in this case, you don't want to, arouse any type of suspicion by maybe making the type of announcement of, oh yeah, guys, we discovered there's an issue with our proxy. The moment you actually make that announcement, you have 10 to 20 hackers looking at that contract, trying to find what issue you just mentioned. That's the issue. That's the funniest thing. So you just outed yourself. You just told them, oh yeah, we have an issue in this contract. Please help us to hack it. And yeah, they are going to do that. Trust me. So yeah, that's the best way to go. So suppose anyhow a proxy got some logic issue which was not figured out while deploying, then we have to tell everyone to take their money from the protocol. Just like I said, if the type of issue that occurs is one where you don't have the luxury of time, the first thing to do is basically just get all the cash out of there. Then you can focus on how to refund users later, if you get what I'm saying. Because the blockchain ecosystem is basically, it's a dark forest, right? Everyone is out there to get everyone else. So the moment you share announcements, the moment you say, oh guys, we have an issue in this contract, we'll be posting the contract, people are looking at it. People have bots that are waiting. People have like bots that basically send transactions faster than you can blink your eye. So most of the time, people just keep it down. They keep it down. Most of the recoveries that have happened in crypto have happened in secrecy. That is white. They call them hacker rooms. That is, you basically just invite the people in that protocol to basically a war room, a private room where you have trusted people, and then they try to get the funds out first. After that is done, then they now come to the public with a post-mortem. That is after the funds have been removed. So you have to think first. Does that make sense? Yes, any contract or chain is part of an audit contest. Exactly. That's it. Everyone is looking at it. Vijay, you have a question?
Yes, thank you for this. I was wondering, you said that proxies are where storage is, right? Where my state is stored. So
Yes.
I was wondering, let's say I forgot to add a field in my struct. Then how do I upgrade that then?
Okay, so the question you asked is, let me see if I can use this to explain. Okay, say for example, you have this in your proxy and you want to now add another state variable. Now, you can actually do that. The reason why you can do that is storage is incremental. For example, if you have a contract that has the state variables, that means owner is stored at slot 0, right? And total supply is stored at slot 1, right? So let's assume you want to add maybe something like a string at slot 2. You can do that, but you would have to include that here in the new logic contract. And it must actually be after total supply. It must not be after owner or before owner. No, it must be after total supply so that you do not cause a layout collision. Hence, what happens is that on the proxy, you would now have owner, total supply, and that's new string. And that is fine because on the proxy, there was nothing at slot 2 to begin with. Does that make sense? So basically, slot 2 was empty before, and now the logic contract is now writing to slot 2. Yes,
cool.
You can do that.
I think I sort of got that. My question was, let's say I did not have this. I had a state variable. Let's say it was an array of structs for now. All right. So let's suppose I had a struct which took the user address and it took the user's balance, and I wanted to now add the username for some reason in that struct. Can I do that here, or do I have to redeploy the contract?
Yeah, for structs, right? You can
Yeah.
extend structs. Actually, you can actually extend members of a struct. It's a little bit more advanced, though, because it depends on how the struct itself is being defined at the root of that particular contract. But you can actually extend structs. You can,
Correct.
yes. But you also have to be careful, because if the struct actually contains reference types like dynamic arrays, then you might actually just want to like have a different struct entirely, so that you don't risk corrupting storage. But if the struct contains normal types, like normal value types, like address, uint 256, defined types that have a specific what do you call it, size, then you can definitely extend the struct. Yep.
Cool. Thank you.
Yes, Uzai, that's what OpenZeppelin does. They are empty storage gaps that are intentionally left at the end of the storage variables in the proxy. So that's when you want to add more, they have space for them. OpenZeppelin does this by defining an array of, I think, 80 uints, if I'm not wrong. That's like, basically reserves like 80 slots, like 32 byte slots, if I'm not wrong. So yeah, let's continue because of time. You know, we're at like slide 9 out of 25. So let's just. So one framework, 4 patterns. Well, let's talk about different upgradable, patterns. We have a lot of them. Let's skip this and go to the transparent proxy. Now, the transparent proxy basically is the EIP 1967. It's basically one of the EIP's improvement proposals, and the implementation is stored in the proxy itself. That is the address itself. Like the address of the implementation is stored in the proxy address, of course. I mean, the proxy needs to know the address of the implementation. But when it comes to EIP 1967, there is something called the implementation slot. It is a defined slot number where for every proxy that implements the transparent proxy pattern, you will find the address of the implementation at that particular slot. Does that make sense? This is for 1967. Now, who is the person that upgrades? The admin. The admin calls the upgrade to function directly on the proxy, and other users that interact with the proxy are forwarded to the implementation. Remember, that is what we talked about when we talked about the dispatcher. Now, what are the common failures that we see regarding 1967? An admin can accidentally trigger an app function instead of the upgrade path. I mean, this, I don't think this has happened before. This is actually one of like the most used proxies, 1967. It's like one of the first and the most used ones. You see them if you look at the one I showed you. This guy, yeah, it's 1967. This is 1967. So we already have an example for 1967. And I think something I actually also wanted to show you guys was, I don't know if this is going to work, but it's the storage layout viewer. I baked it into the tool, but I mean, it's buggy, right? But I'm assuming it should work a little, right? And to some extent. Just give it a second. Take some time to read the storage slots, and then it will give you, oh, yeah, it works. Actually, that's nice. Okay, nice, awesome. So this is EIP 1967. It's a transparent proxy. And as you can see, this is the layout in this case. You can see it stores the name at the 004, that's the fourth slot, the symbol, the decimals, currency, blah, 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 blah. And then finally, it's weird. This is supposed to be the implementation address. This is giving me OX000, which is weird. So I will assume my tool is buggy at this point. I might have to look into it. But yeah, it is supposed to actually store the implementation at a certain slot. That's the address of the implementation in this case. But as you can see, this is what the layout for the proxy looks like. You can see we have the state variables and blah, 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 blah. But we have to look more into this guy. This is not supposed to be empty. So, but that'll be later, right? Not on the call. So let's continue. That is for 1967. An example is the USDC token. Here's a, oh yeah, I think implementation slot is OX36089 and ends with BBC. Yeah, I think my tool is wrong here. Yeah, it was reading the wrong slot, I think. So I'll fix that, don't worry. Okay, so this is basically what 1967 looks like. You have a constant implementation slot, which is, as you can see, catchcack implementation slots -1, and then you have the admin slots, which is also defined, and then you have a modifier for admin. If the person calling, if the person interacting with the contract is the admin, then sorry, run the code against the normal proxy. Whereas if it's anybody else, then just trigger the fallback using the dispatcher. Then you have the upgrade to function, the one we talked about, that allows the admin to set a new implementation address for the proxy, and so on and so forth. That is 1967. It's the simplest form of proxies you can actually come across. Let me see if there are any questions. What tool? Satya, that's my tool. I was actually building it. It contains a lot of stuff, but I will soon deploy, right? I mean, I deployed some this morning, but it's a little bit still buggy. So I need to, make some changes and stuff. It also allows you to like do some simulations, which we might try to do now, but yeah. So Igodaro Daniel, you have a question? Your hand is up.
Timlane, just one thing. This green mark appears on the screen.
Oh yeah, forgot to remove it.
Yeah, if you could.
Yeah,
Sorry.
one second.
Yeah, thanks.
My bad. Give me a second.
I don't want people to think that's part of the code, It's like,
yeah, I forgot it was there. Yep. Okay. I assume someone wanted to ask a question. Yeah, let's just continue because of time. So let's go to UUPS. Yeah, UUPS, the Universal Upgradable Proxy Standard. Now, before we continue UUPS, another exercise, I need anyone to give me a sample contract that is basically a UUPS, EIP 1822. The previous example we were given, the USDC contract, is basically 1976. So I need someone to give me a sample for 1822. 1822, yeah. So while I'm waiting for that, where is the implementation address stored for the UUPS contracts? Same thing. It is where else would it be stored? They're actually stored on the proxy. Proxy is actually the proxy. Normal 1967, the upgrade logic lives on the proxy. You can see the function here called function upgrade to. It is defined on the proxy contract itself. But for UUPS, let me see if someone has given an example. Come on, you guys can just ask ChatGPT for this. But for UUPS, right, the upgrade logic actually doesn't live on the proxy. So if the upgrade logic doesn't live on the proxy, then who's the person that upgrades the proxy? Now, the implementation contract exposes upgrade to. Now, this is a little bit weird, which means that the upgrade function lives on the implementation contract or the logic contract. Weird, right? So the proxy just delegates to it. That means that you are calling the proxy, you are calling the implementation, not the proxy. Weird. Now, what is the common failure? You can easily brick your proxy. Yes, you can. It's very easy to do that because the function that allows the proxy to be fluid, right, lives on the implementation, which itself is fluid. If you get what I'm saying. That means if you make any mistake when you're trying to like upgrade, then you basically break the contract. Yes, I really didn't know why people would use UUPS. And that was why I said you guys should give me an example. Oh, nice. Someone had sent an example. Let me see what contract this is. This is, I think it's a token, right? Oh, wrapped staked ether. Interesting. Sorry, give me a second.
Hey, I have sent in a link. It is in where I contributed. This will show graphs with all the transaction going through multiple contracts. If you show that, it would be really nice.
Sorry, I didn't get that. Jay, I didn't get that. Can you come again? Sorry.
Yeah, I shared a link. Can you show it? I think this is an open source contribution that I had done earlier, and it shows the transaction life cycle, and it will show UUPS and everyone. If you.
Yeah, nice. So nice. This is actually very nice too. So you have the
share. You might as well share that screen.
Yeah, I'm trying to. 1 second. Share this tab. Yep, got it. Yeah. So this is basically stack trace. You have the stack traces. Nice. And you also have the you also have the type of how do you call this? I mean, you call it the transaction lifecycle. This is actually nice. I personally love stack traces because I mean stack traces actually show you how the call moves like around in this case. So this is actually nice. So this is an example of a transaction trace where a user interacts with the UUPS proxy directly, and then it's a delegate call into the proxy yield. The proxy yield in this case is the implementation address, then calls the withdraw function. Sorry. And then passes the amount inputs, you can call it the argument, and then you have two static calls, that is reading from storage, and then another delegate call, then a normal call, a static call, and then finally delegate call. This is awesome. It's actually very nice. Are you planning to, increase the capability of this guy? Can you hear me? Jay, can you hear me? I'm assuming maybe he can. Yeah, Foundry-VBB vibes, yeah. Give me a second. Well, I think I have something like this, but in my tool, this is an example of a delegate call, right? Where you have someone interacting with a diamond. The diamond is basically another type of proxy and calls the function transfer ownership on the diamond, right? So this loads the address of the implementation contracts called the facet for the diamonds. And here you can, this is supposed to have inline code actually, but yeah, this is weird. So you have all the opcodes, the SLOs, the jumps, the SLO, jumps, SStore, that's a store in storage, and finally the ownership transferred logic, or should I call it the ownership transferred event in this case. This is similar to JS2, except that JS2 is actually very faster than mine. So yeah, this is called a stack trace for most of you that's like might not like. But I'm assuming, Jay, can you also share the link to the tool itself? Or maybe I can just do that to the chat so that, I mean, people can just like easily use it. I will also be sharing it in the Discord. Yeah, nice. Nice work. So let's go back to UUPS. Someone said UUPS is actually cheaper than the normal transparent proxy. I mean, I'm not going to dispute that, but in one way or the other, I prefer something to be more reliable and expensive than cheaper and be prone to errors easily. I mean, that's just me though. I'm assuming everyone else has the same opinion. It's actually easy to break, but then, I don't know. I'm not a fan of UUPS. I don't know if there's anyone on the call that loves UUPS. I don't know. Yeah, Tendali does that. Yeah, I actually took inspiration from Tendali to do most of the work, but I actually use the different engine that instruments the transaction from scratch. So I'll be sharing the link on the Discord after the call, so you guys can try it and of course help me debug. Good. So just like I said, this is an example of a UPS proxy. I just have the implementation, byte memory data, sent implementation, this and that. Then you have the dispatcher here. And the issue is that the authorized upgrade stays in the logic contract. So if anything happens to this guy during the course of upgrade, then you break this guy. That is, this guy becomes a contract that is not upgradable anymore. So hence why I hate UUPS. Good. Now beacon proxy. Beacon proxy is I mean, most people don't know they are using this guy, even though they're actually using it, because it's not so common. So as usual, guys, you guys should actually help me find an example of a beacon proxy. I'll be waiting. So now for beacon proxies, right? Where is the implementation address stored? It is stored in a separate contract called the beacon contract, which the proxy reads on every call. If you understand what I'm saying, that means instead of the address of the implementation being stored on the proxy contracts, it is stored in a separate contract called the beacon. And anytime the proxy wants to make any call, it has to read that address from the contract first before it delegates to it. That means that the beacon contract is basically, the beacon proxy is basically an example of what we talked about when we talked about code reuse, which means that we want multiple proxies to use one implementation. If you get what I'm saying. That means we have proxy A, proxy B, proxy C, proxy D, proxy E, proxy F, and so on and so forth. And all of them are actually reading the address of the implementation from this guy, the beacon. So one second. Yep. Sorry, I think I must have. Okay, good. Now, who is the person that upgrades? Say, for example, you want to perform an upgrade to proxy A, then the beacon owner calls upgrade to once on the beacon, all proxies instantly used in the implementation. This is, I mean, it's as it's, do's and don'ts, it's pros and cons, but if you actually upgrade one, you're upgrading all. That's the issue. Because if we have 4 proxies that are actually using the same implementation, and you make any changes to that implementation, that means you are automatically upgrading all 4 proxies at the same time. It's good, and it's also bad. It means you have a single source of error, right? So that means if your implementation has an issue, then you have that issue duplicated across 4 proxies automatically. It's also, a good way to save gas. instead of deploying 4 different implementations, you deploy just one, and 1, 2, 3, 4 proxies already use that guy instead of redeploying 4 times. Now, common failure. If this guy is compromised, everyone is vulnerable because everybody is actually looking up to this guy for the implementation contract. So if the beacon, I mean, that's why it is called a beacon. A beacon is basically a call, something you look up to. So if it is compromised, everything that looks up to it is compromised. What are the logics in the upgrade to function? Oh, okay. Sorry, let me quickly go to this example. One second. This is transparent upgradable proxy. I'm not sure if this is a beacon contract. I'm talking about the agent layer. Give me a second. Let me quickly confirm if this is a beacon contract or not. Let's give it a second. Someone was asking the logic in the upgrade to, but I'm not sure which one you're talking about. Paul, sure. Which proxy standard are you talking about? Are you talking about the beacon here or the one we've done already? Transparent. Oh, that's a long way back. So normally you're talking about this, right? When we talk about upgrade, right, it's not really something so crazy, because when you are upgrading, all you are doing is telling the proxy to forward its calls to a different implementation contract. That's basically an upgrade. You are telling it, oh, don't use this implementation contract anymore. Use this implementation contract. Do you understand? So that's what basically upgrading is. That's what upgrade to is. That's the logic. It literally just sets the address of the new implementation in storage. Does that make sense? And when you say upgrade to one core, oh, so is block cap gonna be based on the beacon? No. Block cap is based on the diamond proxy. It's based on the diamond proxy. Yeah, so we have the beacon proxy. Let's look at code examples for the beacon proxy. For beacon proxy, we have contract upgradable beacon, we have the storage variables, and then we have a function upgrade to, which is you just basically setting the implementation. Now, once you actually set this, every contract that looks, or every proxy that looks up to this beacon is going to be using the new implementation address you just set here, right? Now, this is a sample of a beacon proxy that reads the implementation from beacon on every fallback call. That means this is the dispatcher for a beacon proxy. Sorry. So we have address implementation is equals to create an interface for the beacon address, yeah? And then you call the function implementation, which literally just returns the implementation contract address stored there. That means that for every time any of these proxies want to actually, call something, then they have to interact with this guy to get the address of the implementation, so they will know which implementation to call into or delegate call into. Now, that's basically all there is about the beacon proxy. Sorry, I'm trying to run the reason is because we'll still have a lot of questions and I don't want to waste time. So now we have minimal proxies or clones. These ones are these are the smallest type of proxies you can actually encounter. Examples are the safe multisigs, right? Those ones they are clones. So for clones, right, where is the implementation address stored? The implementation address is actually coded into the clones bytecode at deploy time. The entire process is only 45 bytes. There's nothing else, like literally nothing. The implementation address is hard-coded into the clone's bytecode at the runtime. The entire process is only 45 bytes. Now, let me quickly get the. So I just checked for the minimal proxy. The example you gave me was not a minimal proxy. It's a different type. But let me get Gnosis safe. One second. Let me see if I can get an example. I just need just a simple. Okay. Sorry, give me a second. Minimal proxy. I'm trying to get a sample of a Gnosis safe so that why is it so hard to get just like a Gnosis safe sample? It's crazy. Okay, yeah, I think I found one. This is a safe for the AV team. Yeah. Okay, so this is one. I'm assuming this is the previous version. I'll just drop this in the chat. Yeah, you guys are going to go deep dive into diamonds tomorrow. So
Isn't Uniswap V2 uses this?
Yeah, for the peer addresses, I'm not sure, right? Because of the salt ball. Yeah, I think they actually do.
Yeah, and like something like safe also uses it.
Yeah, I was actually looking for a safe multisig. That was what I had in mind. Give me a second. No, it's we're trying to look for liquidity pools or liquidity tokens. But you know what? Let's just continue with this. So that's when we actually get to the questions, we'll actually like find them together. Now, for minimal proxies.
We can also put links in the forum later anyway. So
yeah. Okay. So I actually sent the link to the chat. So supposed to be okay. Temilolua sent a link. Let me see which contract is this. Yeah, this is the factory, right? This is the guy that spawns them. But I'm assuming this is 1.3 or 1.1. I'm not sure because Gnosis actually used like a different should I say proxy standard for most of their should I say across different versions. So some of them might not be minimal proxies. So let's look at an example of an AIP 1167 clone. So it says that the address of the implementation is actually hard-coded into the bytecode itself. And yeah, you have this guys 3D602 80600083D blah blah blah. This is basically just bytecode. And when you actually like look at maybe you decompile it or you look at this bytecode one by one, you would see it's basically just opcodes that look into that fetch and forward the current call to the implementation address that was actually hard-coded into it. So here's an example. We have contract vault factory address public immutable implementation. Sorry. Immutable implementation means you actually, passing the implementation address into constructor and it is saved. It is not saved in storage. It is actually part of the contract bytecode. That's what happens when you use immutable or constant keywords. Then you have the function create vault. This is basically like saves multi-sig create proxy. That is when you want to create a new multi-sig. It's basically you pass in the address of the owner, then it clones the implementation and passes the address of the implementation as part of the bytecode of the new proxy you just spawned. Now, I will still actually get an example of the minimal proxy so that you guys can take a look at it. But that is actually all there is to minimal proxies. They are actually quite common than you think because they are very, very easy to like spawn. When I mean spawn, I mean deploy. So you can deploy like 100 like clones and they would take like a very, very little amount of gas because the bytecode is so lean and so thin in this case. Now, oh yeah, someone raised up their hand.
Yeah. So my
Yes.
question is, can we easily test Proxies like with mock data, the way we test Uniswap, maybe with Foundry or any other tools, just to like confirm that this that I'm implementing is working as expected?
I mean, at all points, right, you can test proxies because let me just take this to this place. If you remember at the beginning of this call, we had this, right? You are the user, right? You are the tester in this case, and you want to test this proxy. You don't really have to do anything crazy, right? Because the contract you actually be interacting with is basically still the proxy. You don't need to do any type of abracadabra, magic, blah, blah, blah. You interact with the proxy the same way you would interact with a normal smart contract. But of course, the main issue is that the proxy would not even contain the code you are trying to test, right? It won't, but it would, show the behavior of the code. If you get what I'm saying. It doesn't contain the code, but it contains the output of the code. That is, any changes that this code makes, you definitely see it being reflected on the proxy.
Yes,
because that's the storage that's been limited here. So of course, there will be some extra stuff that you have to do. For example, you have to bind the API of the logic to the proxy contract.
Yeah.
You have to test for storage collision. You have to make sure that you are not doing anything wrong, but you can still test it the same way you would test a normal contract.
Okay. Thank you, sir.
I mean, we will be doing that. when it gets to diamond, you would see why. But definitely, you can still do that. Yeah.
Thank you, sir.
So let's talk about the security checklist before we actually talk about for diamonds. Sorry, I just talked about diamonds and now I have it. So for proxies, I mean, this actually applies to literally almost all proxies, if not all, just almost. Marco Pezzo. So, okay, maybe I will just look at the chats once I'm done with this particular slide here. So now, what are the checklists for this guy? So of course, always protect the upgrade function every time. Most people might forget to most people might be like, oh yeah, that's a very simple thing to do. I can always, trust me. No, you can't always, because most of the acts that happened 2022, 2023, should I say, were as a result of unguarded upgrade functions, initializers that forgot to actually add modifiers that should, stop them from being called twice. Funny reasons. I mean, you as a developer will be like, yeah, I mean, why would someone make this mistake? But trust me, it is actually very easy to make. So always protect upgrade functions, always. Protect them. Anytime time you have if you write a function that is going to make changes to that particular proxy, they have to be guarded. Always use an initializer. I mean, OpenZeppelin templates already have this baked in, so you don't even need to implement this yourself. You can just use OpenZeppelin's contracts in this case. BLOK reinitialization. What the attacker did was, I can't remember what it did. I can't remember, but what it did was, because normally when you upgrade a transparent upgradable proxy, you get an event that is being emitted with the new address of the implementation. Most of the teams actually have tools that check this event to make sure that the upgrade was actually successful. But the attacker was actually very, very sophisticated in such a way that he was able to actually spoof this event to actually give the correct implementation, and then still even though the implementation address was actually the wrong one. It was actually very sophisticated. I wish I can actually get the tweets, because I mean there were some tweets, but it was actually very nice. It was like an Etherscan spoofing, because Etherscan actually shows Etherscan uses the event emitted from an upgrade transaction to check allow teams to check that their upgrade was actually successful and they did not upgrade to a malicious implementation. And this attacker was actually able to spoof it. So yeah, it was actually very nice. So back to this guy, BLOK reinitialization. This is actually done here. So you have modifier initializer here. That's actually what the initializer does, just to make sure that you are not able to reinitialize it in the same block. It's basically like a reentrancy guard in this case. 1 second. Yep. So we have append only storage layouts. This was what I was explaining. Only append to the storage layouts. Do not, insert. Always append. So if you want to, include a new variable, make that variable to be after whatever variables were there. Do not insert the new variable between whatever was there, because of course that would mess up storage layouts. Now, AIP 1967 uses predefined storage slots. And I wouldn't say you should do this to some extent, but there's already another AIP that specifies, it is called namespace storage slots. So you can specify a certain storage slot that you want to use for a certain thing. It's like a standard. So that means if someone is looking at your proxy, they already know which slots to look at if they want to maybe get the owner of the proxy, or they want to get the implementation address of the proxy, and so on and so forth. So that's basically what the 1967 storage slots is. Now, test the full upgrade part. This is also very important. This is part of the test we're talking about. When you're actually dealing with proxies, you want to make sure that the full upgrade part is tested. Deploy the first version of the proxy, deploy the implementation, upgrade, then maybe call a function or do anything that is going to make changes to the proxy using the implementation code from the logic contract. Then do your test. Make sure storage was actually changed the way you wanted it to be changed. Do all the checks necessary for that. Do everything. Then deploy a V2 and do your test. And something extra I do is to actually check storage slots and see how far they are from each other. That is something I actually do too when I deal with proxies, just to make sure that I'm not going to be dealing with them, even though it is nearly impossible to happen, I'm still very, 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 careful. And finally, emit events. This is actually the most important one. Always emit events on upgrade. This is built on the solidity rule, which says you should always emit events on every state change. But in this case, all emit events for your upgrades. Always emit them and index them so that you can easily pack them with an indexer. Now, let's compare these guys to each other, right? For the transparent, right, the implementation is stored in the proxy. This is just like a recap. For the transparent upgradable standards, the implementation is stored in the proxy contract itself. It is the admin, that is the admin of the proxy contract, that upgrades it. Definitely upgradable, and it is higher gas to deploy. UUPS implementation is stored in the proxy. Sorry. And it is the implementation that, implements the upgrade itself. It is easy to break, remember, but lower gas. Now, the beacon contracts, what we talked about, the implementation is stored in a contract called the beacon contract. And remember, because the implementation is stored in the beacon contract, whoever owns the beacon contract is also the person that is able to upgrade all the contract at once. So that means the upgrader is the owner of the beacon contract. Whenever you upgrade the beacon contract to have a new implementation, all proxies that depend, or should we call them beacon proxies? All beacon proxies that depend on the beacon are upgraded at once. And of course, it is low to deploy. Low gas. And finally, clones. We already know it. Implementation is stored directly in the bytecode. It is not upgradable. I mean, at this point, you are storing the logic. Sorry, you are storing the address of the implementation in the bytecode itself, which means you can't change it, right? That means whatever you have defined in the implementation is basically exactly the only logic that will be defined throughout the life cycle of that proxy. And it is the lowest to deploy, 45 bytes. I mean, it's just pure bytecode. Now, simple, I think I actually forgot to complete this, but if you want simple upgradability, you choose the transparent or UPS. Like I said, transparent is safer, very safer, because with UPS, you can actually easily, break your contract, definitely. And if you have a lot of instances, and when I mean instances, I mean proxies, use the beacon contracts, especially if you want to upgrade them all at once. But you have to be very careful security-wise, because in this case, an upgrade to the beacon is an upgrade to all the proxies that depend on it. And if you want a lot of many cheap instances and you don't need any upgrades to them, use clones. An example was the one Jay talked about, which is Uniswap pools. That is the pool contract for token pairs. I mean, there's no point upgrading those, and you want a lot of clones of that, and also Gnosis saves. Even though some Gnosis saves actually support upgradability through modules, I think the first versions actually used clones, the minimal upgrades, minimal proxies. So yeah, of course, the last one now. Just before we get to the last one, I just want to give you guys this. So namespace storage layout. This is a new EIP that was just passed, and it allows you to define struct-based namespaces. The DAMO standard actually already does this. It does this very, very well, and it allows you to define or to define your layouts using a struct, and then you actually set the beginning or the should I call it? You set the slots. Should I call it? I wouldn't want to call it slot offset, but let's call it slot offset. You set the slot offset at a certain place in storage. just to, I mean, EIP 7201, the main purpose of EIP 7201 is to actually stop storage layout collision. That's all. That's basically all. Because in Diamond, you can actually tell them to start from slot 0, or you can make them start from a certain namespace place in storage. But this is a standard. So I would advise you guys to like take a little look at it in your free time. Then, of course, we have the 1967 one we talked about, 1822, UPS, minimal proxies, diamonds, and open Zeppelin operators. Now, regarding diamonds, I'm not going to be using this guy for now. I'm going to be giving you a very, very brief intro because I mean, tomorrow you are going to be diving deep into it with the creator. So yeah, there's little I can do. So before we dive deeper into diamonds, any quick questions regarding what we've done? I mean, there's a lot of chats here. I don't even know where to start from. I mean, the chats are more like discussions instead of questions. So, I mean, I don't think there's much I can do here, Shipao. I mean, if you look at the chats, it's basically just discussions, right? It's discussions. There's little I can do. I can't. If you have any questions, just this is the time. How do you measure storage distance, especially when you have dynamic values, right? Okay, so, well, I don't specifically measure storage distance. I measure touched storage distance. In Foundry, you have something, you have one of the cheat codes called, I've forgotten. It's called access. Accesses. I think it's called accesses. And what it does is that for a certain call session, it enumerates all the slots that were touched in that session, right? So if you know that this slot was touched and that slot was touched, that is, maybe it was written to or read from, then you can basically know that, okay, we have slot 2 that we wrote something to, we have slot 50, we wrote something to slot 50, we wrote something to slot 89. Then you can measure the distance between these 3 slots, right? And see how far they are from each other. Do you understand, David? So that's basically, I mean, the test itself is not really useful to some extent, right? It isn't. But in one way or the other, it gives me like, oh yeah, I'm sure that these guys are far from each other. I always make sure they are like 100,000 slots away from each other. I mean, even the normal solidity when deriving mapping slots with keys, it still gives you a random place in storage. So it's still the same thing. Do you understand, David? Okay, nice. So I think there was another question. Can you explain the underscore gap variable used in upgradable contracts with example? Yeah, example would be me looking for, give me a second. One second, please. I'm trying to find the, okay, so this is from Open Zeppelin's documentation. So I'll try to find where they define underscore gaps. Okay, so yeah, now look at this. So we have contract base, and in this contract base, at slot 0, we have U256 base 1. That is, we have a number, a 32 bytes number stored in base 1. I'm stored in slot 0. Now, slot 2, sorry, well, let's just say slot 1, slot 2, not slot 0 and slot 1. In slot 2, right, we have we can't call this a reference type, right? Because this is not a dynamic array. This is basically a static array because you already know the size. And what happens when you define static arrays in storage? Can someone tell me what happens when you define a static array in storage? You can unmute, you can send a message to the chat. Okay, David says it's defined multiple times. Yeah, you are correct, but that's not the word I'm looking for. I mean, that's basically what it does. But I want it in a more simpler word where everybody would understand like what happens. It's assigned to a slot. Yes, every variable is assigned to a slot actually. But what happens when you define a static array? Say, for example, you define an array that has 50 elements. What happens? What does the compiler do? Come on, you guys got into the Cohort. You know exactly what happens. It's assigned to the next 50 slots. Ah, interesting. Okay, so everyone is saying that Temilolo says it assigns slots to each element. Jane says for each slot, we have different, we have the incremental elements. Ketchkak, Chowdhury says Ketchkak. Interesting. Misha says sequential slots for each. And let me see. That array must be different from just zeros. Of course, I don't know. I don't understand that, Kumar. Yeah, but this is what happens, right? When you actually define something like gap, the next 49 slots are reserved for gap. That's exactly what happens. It's like, you know, you go to a restaurant that has maybe 100 tables and you reserve 49 of them. That's exactly what that was. So do you guys get that? Yes, Jane. Normally when you have unit 8, unit 32, if the next value after that variable can still fill up. I mean, if you look at this tool, right? Give me a second. Oh yeah, I don't have the contracts anymore. Oh, let me just check it again. Give me a second. I just want to show you storage layout. I think it should be easy to use that to explain. Okay, so I'll just wait for that to load up first. Where's the tab here? Okay, got it. So I'm waiting for this guy to load up the, okay, good. I think I found this. No, that's not what I'm looking for. Okay, nice. Okay, let me share this tab. So now take, for example, the storage layout of this transparent upgradable contract, right? From slot 0, we have slot 0, slot 1, slot 2, slot 3, slots 33, 34, 66, 67, 98, 99, 98, BBC, and this 103. Oh, this was the implementation slot I was talking about. It fetches the correct address, so it's well. But now let's look at this slot. Let's look at this slot that has how many variables? Can anyone see this? How many variables does this slot have? Slot 33. Two, good. So this slot has sorry, let me get this. This slot has two variables, and one of them is a unit 8, the other one is a Boolean. Both of them are actually 8 bits, right? And if you look at the way it is, you can see that the first 31 bytes are unused. Like they're basically unused. And they're actually packed to the end, where you have underscore initializing and underscore initialized. 1 byte, 1 byte. That means you have 30 bytes, literally unused. Now, regarding underscore gap that we talked about, you can say that in slot 3, we have underscore gap being defined, right? Isn't it? With 48 values. And that means that the next value or the next variable that was defined started at 33 instead of 4. Does that make sense? Note that this 33 is not decimal 33, it's hexadecimal 33. So that's basically 48 plus 3, which should give you 51. So this is 51 in decimal, if I'm not wrong. Do you understand gap now? So that means underscore gap u into 5648 has reserved the next 48 slots. Same thing happened there from 67 to 98. Instead of this to be at 90, at 68, it started at 98 because the next 49 slots were reserved. Same thing happened there. Does that make sense? I think that is more visual.
Timberland, I think people were just asking, why have these back gaps? Just explain to them.
Sorry,
I can see on the channel, people are asking, why have these gaps? Why have these buffers?
Okay. Why is gaps declared on the implementation and not on the proxy? Are you sure? Give me a second. I'm trying to get an example here. For example, this is the proxy, by the way, not the implementation. You understand? Like this contract, OX AOB, is the proxy. This is not the implementation. This is the implementation address, OX519. Do you understand? So they are this is on the proxy, not the implementation. And to answer the question of why exactly do we have gaps? Like why are we reserving space? Because we might decide to, add some variables between. If we reserve gaps, then we can easily do that. I personally don't like that. I mean, if you want to actually extend storage, just append storage, simple. There's no point having, oh yeah, we have 49 free slots. We want to post in something within, no, that doesn't make any sense. It's actually easier to make mistakes that way. So, I mean, with Open Zeppelin's library, of course, you can't easily make mistakes. I mean, they have helpers that help with that, but then it's too inefficient for me. So instead of that, just append, simple. Yeah. Yeah, so before time has gone actually, but we actually really need to talk about the diamond standard. I'm going to be using, give me a second, sorry. I need to quickly get a contract address from here. Okay, got it. So now let's talk about the diamond standard. I'll be using my tool to explain it because of time. That way we have visual representation and stuff, I guess. Oh, yeah, I already have it here. So, Good. So this is a diamond contract on base. And as you can see, it's even after fetching the contract details, it still needs to fetch some things called facets. Now, see facets as implementation contracts. The main difference between the diamond standard proxy, like the proxy standard, and all other types of proxy standards is that you are actually allowed to have multiple implementations for the diamond proxy, like multiple. You can have hundreds, thousands, millions. Well, there's no point having millions, but you can have hundreds. For example, this diamond has 33 different implementation contracts. Now, why exactly would you want a proxy to have multiple proxies? Well, for example, take a look at this diamond, right? This diamond has it has an implementation called the DAO facet. And the DAO facet contains functions like that are DAO-y in experience, like functions that actually lean more towards DAO stuff. You know, functions that a DAO would want to call. It has functions regarding, you know, maybe item transfer, ownership, and so on and so forth. This means that you can have different functions for different things in different contracts or different logic contracts. And everything is being called via this diamond. If you get what I'm saying, everything is called through the diamond. Everything. So now, if you want to interact with a certain facet, you call maybe the DAO facet. It would basically use the same dispatcher we talked about to dispatch the call data to the specific facets or logic contracts and just give you back whatever data you want to do. So let's say we are trying to read some stuff here. Get forged diamond. Good. We get our output. And the final thing I'll be doing is I'll try to simulate this instead, so you can see how this goes. It's basically like a way for you to, you know, see it visually. So just give it a little bit of time. It's going to take a while to, you know, fetch the facets and blah 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 and blah. It's a long time, but give me a second. I can just use the call data directly, right? So I can just use the call data. This guy. Okay. So we have no. I actually need a function from one of the facets. So I will have to wait for the facets to. Yep. So let's call a function like DAO facets and get forged diamond. So this is the core data we just have to implement against it. But so we come here, we select the diamond we want to interact with. We select raw input data. Then we input the raw input data that we actually have. We don't need to impersonate. Yeah. And yeah, we simulate. So this should take, I think, like 10 or 15 seconds. While we are doing that, let's just continue with this guy. So you guys are saying you don't have any questions. Okay, so Paul, you might be getting a little bit confused, but is there a difference between implementation contract and logic contract in the context of diamond patterns? No, there isn't. You see, in diamond, you can either call them implementation contracts, logic contract, or facets. They are the same thing. I mean, it's basically just linguistics, but they're actually the same thing. If you get what I'm saying, like it's the same. There's no difference. Can we choose which facet to call if multiple facets have same function selector? Now that is, I'm not supposed to say this, but it's impossible. You can't have multiple function selectors in a daemon. The daemon literally protects against that, because the only way for the daemon to know where to dispatch a function call is to know which facet contains the function selector. So imagine you have two function selectors that are the same. Then the daemon wouldn't know where to actually dispatch it to. So yeah, my brief explanation of the daemon. Give me a second.
I was going to say, Timoleon, let's let Nick carry on from there. I think.
Yeah, exactly, because
he's done a fantastic job of running through proxies. I think as a cohort now, exactly, yeah. Actually, Timoleon, I'll take full screen for a minute.
Okay.
I don't know how to do that again. Everyone pin.
1 second. Yeah.
I think you have to go first, and then I come in. Hang on. Let me just try pin to screen for everyone. Yeah, I think Timoleon has done a great job for you all. So now as a cohort, you've got plenty of questions to ask, and I think let's use Discord to do that. Everyone, you know, Discord is the home for the cohort. It's your new home. So please go to the forum, ask away. You know, you're going to deal with professionals who know this back to front, and enjoy yourselves. Deep learning now, guys. This is the moment. So I hope that helps.
Nice. Is that the, because I mean, just give me a second. You guys should check this. So our simulation is done. I just wanted to just show you guys the life cycle of, like, you know, interacting with the diamond contract. So if you remember, the function we called was the function get forged diamond. I'll be very fast. And this was us. This is us. We interacted with the diamond contract, and we called the function get forged diamond. And the output was this address. But this is the life cycle, right? There's an S load here. An S load is basically you loading from storage. And this Nick will actually explain what this line does tomorrow. So you can just, for now, look at this. And yeah, finally, you have a delegate call. The delegate call is basically the diamond delegate calling into the facet, because it knows that the facet contains this function we just called. It didn't delegate call into the shop facet, no. It's delegate called into the DAO facet, because the DAO facet contains this particular function that we just called. And the facet gave it this output, basically just by, you know, loading it from storage. And there you have your output. So yeah, this is the complete stack trace of a diamond call, and you can see everything. So yeah, that's all.
Okay, guys.
I'll try my best to make it public, but yeah, that's all.
No, we'll definitely make things more public. Listen, let's give a big round of applause to Timoleon. I think he's done a fantastic job there. Honestly, Timoleon, well done.
Thank you.